Today's video is going to be about wiring up a fan motor and utilizing the relay of choice, a one-pole contactor. One-pole contactors, this may seem like, hey, look, why am I going to watch this video? I know all about one-pole contactors, but I'm going to show you what you may not know about them. Stay tuned. We're going to discuss relays and how we can use them for blower motors. There's all types of relays out there. One of the most familiar ones would be a contactor. We have a couple of contactors on our CANTEX box. We're going to utilize the one-pole contactor today, and then other videos we'll get into these other relays that you see here. So we're going to go ahead and apply power, and then we're going to talk about the power supply that's on this CANTEX box and what our goal is to do. So we're going to go ahead and just get everything powered up, and I'm going to demonstrate how much power is sitting here. My meter has a backlight. We should be able to see that right now we're at 0 volts. Between R and C, move my arm out of the way, we should be able to see 27.7 volts. And between L1 and L2, we should read the difference of two legs, giving us 241 volts of electricity. And then obviously the goal is to get the light to come on, and this is only going to come on once T1 and T2 are energized. And so those are familiar terminals. We typically see those terminals on condensers, on air handlers, schematics and whatnot for HVAC. So when I go to bring this on, I'm going to do it first without a relay, and then I'll discuss how the 120 volt light only works when we apply 230 volts of electricity. Go ahead and connect L1 to T1, and I'm going to touch it and you'll hear a click because I have a contactor inside my box, some transformers, and once I've energized T1 and T2 as a combination, then our 120 volt magical light will come on. So we'll hear the click and the light will come on. Right? And so what we're trying to do is we're going to break one leg at all times. And so I'm going to show you something though. This is pretty interesting. You can see how I have color-coded one leg of power and I've color-coded a second leg of power. What I want you to see here is that the 230 volts of electricity that I have on L1 and L2 down here, or excuse me, 240 volts of electricity, it's the same as I have up here between T1 and T2. Now, once we break that through a relay, we're going to lose that voltage. So let me go ahead and explain the one-pole contactor. As you see, I'm not breaking any legs of power. It's just literally from L1 to T1, L2 to T2. But if I were to come around and take any one of these off, we disrupt the 240 and the load shuts off. Now there's still power on the load, okay? It's just not enough power to energize the load. So I'm going to now come through the one pole contactor, and what we're going to do is I'm not going to break any voltage because the pole that I'm using has no switch on it at all. So it's just closed. It's always closed. It's just a bar there. And once I hit T1, you'll see that we have power. And that's pretty much what a one-pole contactor does, is it always supplies power on this one side without any coil voltage. We take T2 and we come down to the bottom of the contactor here. Then we come out the top side back to I'm sorry, we go to L1 here on the contactor and we come out the top side to T2. Okay, we don't have 240 volts until we push the contactor in. And so we're going to control this with 24 volts, which we have up here between R and C. I'm going to go ahead and connect the 24 volts to it. And we're going to run common first. Not that it matters. I can run either one. Just working from the right to the left here. We'll come over here. And one pole contactor is a very easy contactor to teach. However, it's more complicated to teach a one pole contactor than it is a two pole contactor because you have to teach a little bit more electricity. Because what happens here is I always have power, right, present between one leg, because I'm only breaking one leg. So the other leg is going to be present throughout the entire circuit. So let's look at what our voltage is. I'm going to go ahead and leave one lead on T2. And then I don't have a whole lot of sources here for ground. So let me get creative here for a second. If I were to use a ground. Okay, so you can't really see everything in my lab, and that's all right. But I'm gonna make an extension on my lead with an alligator clip, and I'm gonna run over here to a source in my lab that I know is grounded. I'm gonna test that real quick, see if I have one leg of power, and I do. See how I have 120? So I'm gonna show you now that if I lose power, oops, my ground fell off. Let me fix that. Okay, do that one more time. There we go. All right, so and so all we've done is matter of fact, I'll just go ahead and take this green wire off too, just to clean it up a little bit. So you can see once I push the contactor in, we have a full 240 volts, right? Because we're only breaking on this one side, right? But I want to demonstrate that there is power here, there's power here, there's power here, and check that out. Now, how am I going to have power here, of all places? Now, check this out. I'm going to push the contactor in. It's still 120. Contactor pulled out. It's still 120. But I want to show you what leg am I really using. Now, we've already said this is L2. We've already said this is L1. I'm going to show you what leg we're running. I'm going to go ahead and unhook my ground. We're going to not be able to read any voltage. Okay, now I'm going to show you here. If I read across the top side of this contactor, you're going to read 0. If I read to the bottom left side of this contactor, you're going to read 0. Now watch this. 240 volts. That is because L1 is present all the way through on the yellow, all the way back up, and then all the way through my load, okay, back to T2, okay? And so if I said this is L2 down here and T2, you will read 240. Now, the moment I push my contactor in, you will read 0. See that? Because I'm on L2. The moment I drop my contactor out, I will read the sum of L1 and L2. And that's how a one-pole contactor is more complicated than a two-pole contactor, because when you have a two-pole contactor, you're breaking both legs of power. And I want to give you a fine respect, because you could take a technician who thinks they're pretty savvy. And it's funny when you can throw a simple one-pole contactor at them, and they'll sit there and they'll probably lose their cool if you're messing with them, because they're going to realize that they don't understand open and closed, and you know, how one leg is always present no matter what. So like I've shown you in other videos, whether it's the heat strip or the first video we released that has to do with motors and relays, just because I'm reading 0 with my meter, that does not mean there's no power, because I will get electrocuted if I touch that. So we're going to take it to another application where I take this one-pole contactor and I'm going to put it on a motor, and I want you to see the motor run using a one-pole contactor, and then we'll take it to the smart board, and we'll utilize it there where I can draw it up, and we're going to continue to express one leg of power that's being broken and one leg of power that's always present on everything, and hopefully that sharpens your diagnostic skills. Stay tuned. Okay, so now we have a more practical application where this relay, the one-pole contactor that we're using, today's relay, we're going to use it for this motor. This is a little bit more practical. A lot of people, I don't think about using a one-pole contactor. Remember I told you in the other videos, you only have to break one leg of power, whether it's for heat strips or motors, it doesn't matter. Your load can have the other leg present, because if the load requires the full 240 volts of electricity, then when it still has one leg of power, that's only 50%. That's not enough for it to energize. Not unless it shorts the ground. It may run at a half speed or something, which is not good, but which we could cover in other videos. That I think a lot of people look at the one-pole contactor and they don't really appreciate it to its full value. It's not my favorite to use as a blower relay because it's loud. I don't like that loud click. You know, it might echo through the ductwork a little bit, especially if it's a metal duct system. It's basically like blowing through a trumpet, right? You know, you can already hear the air, so imagine a click on top of it. That could be a little annoying. But past that, if that's all I had on my van, because I'm probably going to carry a contactor for my AC unit outside, if I only had that, I want to show you how that would be very useful if you had to either convert an ECM back to a PSC, or you're working on a PSC and you need a relay. So I want you to think outside the box and go, yeah, it's a little overkill as far as the points, how much power they can carry, but it doesn't matter. Your job is to make sure the fan can turn on and turn off based on a G call. And so we're going to go ahead and demonstrate power. We're going to demonstrate where power is present when it's not getting a G call and when it is getting a G call. I have a ground source. I bought an extension cord over here just to use for ground my power supply. I'm going to hold it up and kind of explain that we use this for all types of lab stuff that we do in our classroom. But right now we have a live line voltage of 2 legs of power, just like I had over there where the light bulb was. As you can see here, this is another light. And basically, I'm not trying to use this to get my light to come on. Yeah, I got a transformer down here providing 24 volts. I'm just using this voltage so I can energize this motor with a live 240 volts. So it's allowing me to do other things with it. So getting right into it, let's look at the power. Okay, I'm going to go ahead and show you that there's 240 volts or 230 volts, sorry, 237 volts of electricity. And down here we have a 26.8 volts on our low voltage side. And let's test our ground out real quick, see if we can get 120. Yep, both legs are showing. So just using one lead inside of here, I should be able to leave that in there so I can show you how there's still power present on all these other legs I'm sorry, not legs, but speed taps when the relay is in the open position, not allowing the motor to come on because we're only braking one side, the other leg's gonna be present all the way through. And I really wanna demonstrate that. I think that's a confused thing in our industry that, you know, I don't think we dive enough into it to get that respect. Okay, so to wire this up, we can do it first without the relay, and then we'll do it with the relay. I'm gonna try to color code this to make it easier. I'm gonna go ahead and put line voltage on the white, and as you notice, I don't have it on anything else, right? So I'm gonna show you right now, where do I have power? Put that one in the ground. Okay. Give me a second here. Okay, that should stay. All right, so let me show you where I have ground. Or sorry, 120. So I should be showing 120. You can turn the light back on. 120 here. And I'm going to show you that there's nothing hooked up to these other ones. All I've done was hook up one. And when I touch each one of these, you'll also see 120. So what that means is if you don't understand the path of electricity, you know, you can mess some things up. So you really want to study your path of electricity. We go over a lot of this stuff extensively, so you're going to learn quite a bit. And I'm going to show you with two leads. If I were to touch one here, now I just demonstrated there's 120 volts on every one of these speed taps, but when I go to touch them, you will read 0, 0, 0, and even here, 0. That's because I'm on the same leg of power. And so when I take that and I go across my relay, you're not going to see anything different. So I'm going to go ahead and come up here, and I'm going to go across our relay. And bring this back down to, excuse me, our power supply. And I'm going to show you that we now have 240 volts or 235 volts of electricity here. We have two legs of power present right now, right? And so right now we know the energy, the relay is not energized. So what is my power supply here? Right? And so once I put, you know, these terminals back to it, because through the motor, we're going to have a path of electricity right back to the opposite side of the relay. And so if we were to take and start energizing motor taps, I'm going to try to stay on the same colors here. I'm going to pick medium speed, which is blue, where you would normally wire it to. And we're going to take the side that we're not braking, and we're going to hook it over to the other side of the motor, which is our line voltage. And now once we push our contactor in here, we'll have all three of our windings, our run, start, and our common winding will be energized, and the motor's going to come on. So I'm just going to push it in. And as you can see here, it's running, right? So simply I just apply 24 volts and we're good to go. But I want to demonstrate the power. I'm going to go ahead and, as you know, right now, it is not energized with 24 volts, so there's not 240 on my relay, but we know each side of the relay has 120 volts. As you can see here, as I navigate through different terminals on the relay, we are at 120. I'm going to come back over here and you still see 120. And that's interesting because my contactor, right, it's off, but yet I have power on all 4 of these because we're running power through one side of the contactor all the way through the windings and then back up to here. So this leg, this leg, this leg, or these terminals I should say, they're all on the same leg of power. So if I go across L1 and L2, you'll see that I have 237 volts. If I come from the yellow to the yellow, you'll see I'm reading 0. If I go from the black over here to the black over here, you'll notice I'm running 240 volts. I just demonstrated this with the light bulb. It's the same thing, but that's why you have to be careful because, as I said, the relay is not energized. If it was energized, motor's running, right? But if you look here, I still have 120 volts of electricity on these other 2. And that's why you want to put a wire nut on these and safe these off. We're going to go ahead and apply the 24 volts to the contactor just so we can say we did it. And then we should be able to wrap up this portion of the video, move over to the smart board. All right. I'm going to come over and we'll give it common. So we have a path of electricity back and we should be running. Contactor is energized, it's running, no surprise. Now, if I were to cycle through different speeds, okay? There we go. If I were to cycle through different speeds, you'll notice the difference in acoustics on your end. You can't tell by volume of air on my end, it's blowing harder. We can't run all these speeds at one time because they're different windings, right? So there's different resistance on each one of these. So we have low speed, we have medium speed, right? And then beyond that, we have high speed. Now you might be asking, what speed do we normally use? Well, the manufacturers recommend medium speed for cooling, right? That gives you roughly around 400 CFMs of air per ton. And then they recommend typically either medium speed or low speed, depending on what type of heating you're running. If it's a gas furnace or electric furnace or a 2-stage heat pump system with, you're going to have to pick speed up, obviously, get more volume of air so you can get more airflow, so you don't have any issues in your supply air plumb, which we'll cover that in other videos. All right, so that wraps up this portion. We're going to move over to the smart board, and I'm going to show you how to wire this up. Everybody has a different way of learning, so we have adapted these different lab with the smart board, so we're reaching out to everybody's different learning abilities. Stay tuned. We're now at the smart board. I have different ways of teaching. I'll teach you how to wire it up using alligator clips on wires and light bulbs for loads, and how we can pretend the light bulb represents a compressor, a fan motor, maybe just a light, I don't know. And we can have fun. That's how we explore, a very easy way of learning our relays. But when we're trying to find when we're trying to find a proper application, something that you can recognize, what we don't want to do is start talking about these parts in their respected environments. You see that all day long. We want to get everything else out of our minds, get everything else out of our frame. Focus on the component itself. And by doing that, like if we talk about just one pole contactor here, be willing to bet you might learn something new about this one pole contactor that you didn't know. And I like to teach the stuff that you need to know, not everything else about it that you don't need to know. I'm not going to teach you how to build a one pole contactor. We wouldn't do that. But I do want you to know how to understand how to diagnose one of these, which it may be easy to diagnose because you can literally see when it's open, closed, welded, shut, stuck, not making. But a lot of times, there's a lot of wires all over this stuff where the wires have been stretched real tight, you know? And I'll give you an example here. If I had this in its practical environment, then there's a possibility, you know, you might have a hard time learning from me if I'm trying to teach you where, hey, here's a one pole contactor and you have all these wires all over the place, right? But in your world, this is what you see, right? This is what you see. And that starts to make the problem bigger than it actually is. The problem is beneath all that, right? This is a mask, and it fogs up and clouds your judgment. It may even create habits that aren't healthy, like, you know, you may procrastinate or develop habits where you don't check things because of whatever the situation. They put covers over these to try to keep bugs out, right? And so if they make it harder to try to troubleshoot this, and you're not going to go grab a small Phillips head screwdriver with T-stat screwdriver to remove the cover off of this so you can see if it's open or closed. Some of these are covered up where you can't even push them in, right? It depends on which model you have. How do you diagnose this contactor without physically looking at it? Just utilizing a meter. And you'll be surprised that when you can do that, every other relay will make more sense. And those are the things that I really want to home in on this video. Behind me, I have a timeline. That timeline is to help express, you know, where we went from decade to decade, how we evolved to the ECM motor, the electronically communicating motor, coming all the way back to the PSC motor, the permanently split capacitor. As you can see, the number of components that we had back in the 90s and what predated the 90s, you know, up until, you know, within the last 15 years, okay, we've dropped an entire part. And even within the last 10 years, we dropped another part. So in the last 20 years, we've gone from 3 components down to 1 component. When you're trying to troubleshoot something here, it's going to be a little bit more complicated if you don't understand everything before that. And if you did get lucky enough to guess, you know, hey, my motor's bad and I replaced it, and here's how you check it, that doesn't mean that's how you diagnose it. Checking and diagnosing are 2 different things. You know, checking is more of an observation. You know, is it on, is it off? Okay, is it making a noise, is it not making a noise? You know, is it warm to the touch and it's making a noise and the wheel won't turn? Okay, yeah, your motor's obviously needs to be replaced here. There's not a whole lot of diagnosing there. Diagnosing is finding out what the problem is and why the problem occurred so that when you fix it, the problem doesn't reoccur, come back, what have you. That is diagnosing. Service technicians are supposed to be good at diagnosing because they understand a lot. And they know their history typically because they've been around enough to see things evolve, right? And as you know, there's a lot of this stuff still out there on the market that's running and it needs to be worked on. And it needs somebody who appreciates their trade, the company, their team they work for, the client in front of them. You know, somebody who is well invested in knowing things to be able to accurately diagnose. that system. So when I take a simple one-pole contactor and I apply it up here on the timeline, does that mean that it used to have a one-pole contactor? No. Does it mean that it could have a one-pole contactor? Yeah. Does it mean that you could put a one-pole contactor on it today? Sure, why not? You put a one-pole contactor on anything you want. It depends on what you're trying to do, right? And so that's how we have to think outside the box and understand our relays. Also, we need to know how to diagnose using our meter. And so I try to wrap everything up as much as possible. So I'm not just talking about a motor. I'm not just talking about a capacitor. I'm not just talking about a relay. I'm not just talking about how to read voltage. I'm not just talking about how to wire something and memorize it because you understand what's going on. You don't want to always have to just refer back to a schematic because things have to change sometimes. And nobody redraws schematics. Nobody's going to go over there and fix what they wrote down. I mean, people can't go to an electrical panel and even scratch out, what they're using the circuit for, because they renamed it, Panels are labeled wrong all the time. Many things are going to change. And so we can't always rely on something that's not accurate, something that's been changed, updated, or it's not even available because it's missing, right? So we have to know what we're doing. We have to know, you should know enough about air conditioning to be able to buy a box full of components and on the electrical side and just literally just put it all together. Same way on the refrigerant side. When I get to that point and teach you that, you should be able to just take anything and just make it the way it's supposed to be. We have lots of combinations that I can integrate into teaching, right? I have many relays I can use. I have many different fan control boards that I can use. I can simulate every one of these scenarios. So the series of videos that we're going to put out, it's going to be very strong, and like the defrost control videos or the videos that we put out on heat strips, if you go through them and actually watch them, you'll learn quite a bit. I believe your answers are definitely in these videos. I've got a lot of field experience, tons. A little bit about myself to the degree that you could probably appreciate is, like you watching this video, I too yearn to learn about what I was doing. It does take you to greater heights. So definitely continue to one-up your knowledge and continue to pass that knowledge on, because that's what knowledge was meant to be done with. It wasn't being, knowledge is not there for you to, harvest and keep. It's to share. Matter of fact, we got a share button right there on your screen. If you can just share this with somebody that you think it could help, that also helps us. Also subscribe, like, and leave a comment. Somebody asked, what was one of our YouTubers, our YouTube subscribers, asked, hey, what speed, that motor video you did the other day, that was really good. What speed should I wire my motor to? And I said, well, when I make this video, I'll go ahead and answer that. This was a personal conversation, so it actually worked for us. Basically, you have 3 speeds on a traditional PSC motor: low, medium, and high. You can only pick one of those speeds. You don't get an option to run multiple speeds here. So you can pick low, and if you're in cool mode, that's not gonna put enough volume of air on your evaporator coil, so you're gonna have problems with your compressor. You'll have problems with your capacitor outside as well too. And I'm not gonna get into what those problems are because that's not the point of this video. By the time we're done with mini-series, when we start getting into that, you'll better understand, if you follow these series, about how low speed will affect the compressor low speed on the blower. Medium speed is typically what you find because that lands you at 400 CFMs per ton, which is just enough heat to boil liquid refrigerant off. And it's an evaporator coil, so its job is to evaporate, right, in a sealed system. The only way you're going to evaporate liquid is to have airflow. And that airflow has enough heat in it to boil that negative, it's like below negative 60 degrees Fahrenheit. It's like negative 50 something. Not really relevant. Maybe I'll fix that information on another video, but things like negative 54 degrees on 410A, and depending on the refrigerant, it's a different number, different temperature. You don't have negative anything going across your air handler, so there's plenty of heat in that air to boil that liquid refrigerant off. And so the evaporator can do its job, but you have to make sure that you're on the right speed. Otherwise, you're not cooking at the right temperature, right? So we're talking about the stove and the different settings, low, medium, high. A lot of that was referring to blower speeds when I said that on another video. So a lot of people want to pick high speed because they think that fixes airflow problems. It doesn't fix an airflow problem. High speed does not fix an airflow problem. A duct system should be designed at the proper CFMs to deliver the proper tonnage so the space can cool the way it's supposed to. And there's many calculations that are used to determine that. If those calculations aren't used, the numbers are going to be off, the comfort's going to be off, and there are going to be problems. Depending on what region of the United States, there can be major problems if there's a high concern for humidity. And so when we look at speeds, you know, typically we're wired to a medium speed for a reason. You don't want to go from a medium speed to a high speed because that changes the parameters of temperature splits across the evaporator coil. It raises superheats. It also raises humidity in the house. If there's negative pressure, you're inviting more negative pressure in. If there's already airflow problem, there was high static, you just increase the static even more. And you put more risk on the components of failing, you know, because you're adding more stress. You're adding more to it, more job than it can handle. So you have to fix those problems before you just do something like that. So when would you need high speed? Honestly, the only thing I can think of that would actually be a overall benefit would be maybe in the event that the heat pump is on, the heat strips come on. So if I had, like, say for example, say a 3-ton unit, 3-ton heat pump running, and I had 10 kilowatts of heat, that's another 2.5 tons, about roughly 30,000 BTUs or something like that. So, you know, now I should try to get as close to 2,000 CFMs as possible, you know, and high speed's not going to do that. So if I was at 400 CFMs per ton, 3 tons would be 1,200. High speed's only going to give me an additional 50 CFMs per ton. So I'm going to go from 1,200 CFMs on medium speed to 1,350 CFMs on a high speed. So that's a long distance to get me to 2,000 CFMs, which would be 5 tons, just because I have 60,000 BTUs that I'm blowing air across. And so, you know, that's the only time that I could think that a high speed could benefit is in the event the heat strips came on in as a secondary heat source, supplemental heat. And these ECMs, they actually do that. They will rev their speed up. Also, variable speed motors will rev their speeds up too when we actually have those heat strips call with the heat pump. We'll run a higher CFM. And these PSE motors, they're not designed to do that. So you're typically running medium speed, and that's it through the whole thing. So hopefully that answers that one question. When we get down to it, we're going to wire this up, and I'm going to show you between L1 and L2 where power is always present because we're only breaking one leg. We did that with the last video where we talked about a 9380. When we wire this up, it's not going to take us that long because there's not a whole lot to discuss on a one-pole contactor like there was with a 9380. I think everybody understands what part's going to always have power, and we're talking about if I have power here, let me use a different color. If I have power here, I have power here because I'm not breaking a leg. You already know that. I think the disconnect is when you know you have power here, notice I color coded it. What you don't know, if this is open, this power is actually right here. And that's what I want to show you. That's why between these two, you'll read 240 volts because you're reading L2 and you're reading L1. That's what I want to sit here and get you to better understand. Because I believe we've already accomplished on how to wire that up to a motor. So this smart board allows us to thoroughly express what you may not know. So we're going to go ahead and wire this now. And it's not complicated at all. We're going to use 2 legs. I always recommend doing one leg at a time. When you're done with wiring that entire leg, then go to the other leg. And the reason why is the last thing you ever want to do is take power from one to the other, somewhere in the circuit, right? Or vice versa. You don't want to take power to the other because that's very violent, it's very dangerous, and we don't want to do that. The other thing you don't want to do is you don't want to slip up and wire high voltage to low voltage. You don't want to do that. And you can simply do that because if we're calling this common and we're calling that common, somebody less experienced could easily make that mistake. Not to mention, inside your application, we don't know what colors they used. And so you got to keep an open mind when you're going through these videos. All right. So I'm going to wire up my line 2 side first. My transformer, I have load and I have line voltage. Well, if this is line here and that says line there, then, line to line. Now, the load on my transformers is going to secondary loads. So, or secondary voltage that goes to those loads, when we talk about that, we're actually talking about coils, right? And a coil on the contactor here, this is a secondary load. Primary loads would be like motors, capacitors, one side of the transformer. So what we're going to do is we're going to go ahead and just continue, and I'm going to go ahead and break L2, and then we're going to come out of L2 to common. And that's all we have to do with L2. L2 is literally complete at that point. So if I wanted to read voltage, I would read voltage here and here. At this present time, I wouldn't read any voltage here. Not until I start applying L1. So we're going to go ahead and get into L1. I need to power my transformer. So now our transformer has L1 and L2 present, so that's a full 240 volts of electricity. I need to energize my contactor, okay? I'm sorry, my one side of my pole here, so power through the contactor. Now I'm going to come out of my contactor and I'm going to land on one side of my run capacitor, And also I'm going to come out of this and I'm going to run up to my run winding on my fan motor. And the moment I did this, I didn't even complete my start winding circuit, but the moment I did this, I actually had electricity come back through here, and come all the way over to here. So now I have 240 volts because I have L2 and L1 present. See how that works? Let me clean that up. Oops, it won't let me back up that much, so we'll just erase this part. Let's do all this. Okay. All right, so let's see, that went there. That went there. And this came around. To the common side of our motor. Now, to complete the start winding circuit, L1 comes out of the capacitor, right? And it comes over to start. And if you notice that run and start are on the same leg. So everything has been color-coded red at this point in time that is on one leg of power. Everything has been color-coded on the same leg for the other leg of power. Now this contactor right now is still not energized, so I still have L1 present all the way back to here. It's also present back to here because it did this. Here's L1 through my capacitor, all the way to my start winding, back up to my common winding, all the way back over to here. So no matter what, I am technically L1 here until I get power. So let's go ahead and label all these terminals. L1, 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 L1 right now, L1, finally L2. And so L1's always present through all these terminals. And so you have to keep that in mind, because if I were to take my meter out and take my leads and I wanted to read, between L2 and L1, I'll read 240, the same as I will up here, right? If I come over to here, I'll read 0, but if I were to touch it, I'll get electrocuted. And the reason why I'm going to read 0 here is the same reason why I'm going to read 0 here. And so if I read 240, 0, 0, if I went back over to here, I read 240 because I'm reading L1 and L2. So it helps when I label these, because it better helps you understand what voltages I'm going to be reading. Now, the moment I have coil voltage and the contactor pulls in, that's going to change. Let's go ahead and wire the low voltage side. So you saw we did the high voltage first, one leg. We did the high voltage second with this second leg. We went ahead and labeled everything. We went over where our voltages are. Now we're going to wire the low voltage side, because what's happening is I'm trying to work on all these components up here in my air handler, and I can't really see it, or if I can see it, I've got all my tools and my hands in here, and it's a dark spot, and who knows how if I'm bouncing on a bucket or a ladder or whatever the case may be. And what happens is I may be frustrated, my phone may be ringing, I might be sweating, it might be dark, my batteries might be dying on my headlamp. These are real world situations we're in. Customers asking how much longer, your shop's asking you if you can hurry up and get to your next call. And here you are, you're just trying to rewire something because something melted or whatever. The board's bad and you got to put a contactor in it, because that's all you have, just to get them up and running. And so you know, you don't want to be in that state already and be confused on top of it because you don't clearly understand something. So hopefully this helps all that out. We're going to go ahead and come out with 24 volts. I don't like that. I'm going to go ahead and widen that back up. Okay, we're going to come out with 24 volts, which will come out of here. It'll land on the thermostat and then common back to the board, or the terminal block, we'll say, and then out of the terminal block back up to the transformer. So we have output, input, output, input, output, input here, then back out, back to the transformer. So there's my path. And now my first load can energize, and if there's a call for cool, heat, or just fan on, that thermostat's typically always going to energize the G call with any one of these three combinations. So if we were to look at you know what that would look like, we'll say that this right here is our O call. This is our Y call, which is technically the heat call. If it's an O-type valve and that's the only call you get, that'll be your first stage of heat. This shifts the valve into cool mode. I don't have a W here, just like I don't have heat strips, because if we just keep putting everything on the board, then I might as well start adding compressors and crankcase heaters and, you know, pressure switches. I mean, we'll be here forever talking about it. So I'm trying to just add a couple of components to help illustrate what's going on so you understand your surrounding area, but we're really referring to just what is it going to take to get the blower to come on. I'm using this relay, and why is there power on everything? Simple, because you're not breaking two legs of power. And then the G call, using the G call, we're going to come out of our terminal. I'm sorry, let me come out of the thermostat. Let me come out of the thermostat first, and let's provide G call from the thermostat to the terminal block. And then from here, we're going to come over and energize one portion of the coil of the relay of the one pole contactor. And then we are going to have to, in order for that to close, we're going to have to come back up and feed common back up here. So we're going to come out, see how I want to take this wire. I'm going to come this way. And as you can see, that's an input back to the transformer. And so the moment we do this in this application, the contactor is going to close, and now that's going to change where I read W2 at. And so, I'm sorry, W2, L2 at, excuse me. And so we're going to go ahead and erase these two things. We'll go ahead and change it up. We're going to say this is now L2 because with the relay closed, L2 went all the way through, and now this is L2. And that's pretty much it. Okay. We're going to continue to release videos. We're just going to pick a different relay. Once we're done with talking about the majority of the relays out there that you'll find helpful, you know, we're going to get into the fan control boards, fan managers and stuff like that, and then we're going to get into just ECMs being controlled with those boards or relays if you want to. We can have fun with it, and just ECMs. There's not a whole lot to talk about just when we talk about the ECMs by themselves, but all this is on standard air handlers. It's a very large portion of our market in the U.S. Of air handlers that you're going to find on a job site are standard. That's why I chose that particular model. Doesn't matter the manufacturer. You know, the intentions are all the same. Motor's got to come on anytime there's a compressor running, right? So at the end of the day, we're just going to be very repetitive here, but we're going to change up slight things, and Go through them, watch as many as you can. All of them would be best for us. Like our channel, subscribe to our channel. We need the support. Share this with others. Leave comments. We read them. We appreciate you guys, and stay tuned.